Hello again, my name is William Pye, and in this video we're going to talk about symbology. Specifically, what we're going to do is introduce some specialized symbols that will make expressing statements easier, as well as to make determining their truth value easier as well. Now, as statements increase in complexity, having a way to represent them more simply would be a benefit. Moreover, removing the ambiguity of natural language would be useful also. Now, I've been doing this series in English, and I plan to continue to do so, but there's no reason why you couldn't do a series like this in Spanish, Japanese, or some other language as well. So having an object language, something that's apart from the natural language, would be beneficial so you can essentially cross language barriers. But even then, let's restrict our attention to just English. English has several words that have multiple meanings and multiple interpretations, so that causes confusion and ambiguity. We want to remove that ambiguity, so we want to have something that has no other interpretation other than the one that we intend. Thus, we are going to introduce some specialized notation that will streamline and express these statements much more precisely. Specifically, the sentential connectives, each one will have an associated symbol. Specifically, the negation, the conjunction, the disjunction, the implication, and the biconditional. Each one of these will have a different symbol so that there will be no confusion between which one is being used and what is being meant. In so doing, determining the truth of a molecular sentence actually becomes closer to doing arithmetic. It becomes more of a calculation rather than trying to get minced and confused in the words. Hence, one can actually build tables to consider all possible cases that might occur in a particular logical form, thus tying this much more closer to being arithmetic and mathematics. As stated before, a main goal in logic is to create and critique arguments. Thus, a main focus in logic is the truth value of a statement, which we define here. Every sentence has a truth value. It's either true or false. Now, as you might imagine, the truth value of a true sentence is true, and the truth value of a false sentence is false. Now, this is where we will introduce a convention. And that convention is, we're going to use uppercase bold English letters to represent our sentences. For example, P or Q. P here stands for proposition, and Q is the letter that follows P in the English alphabet. Mathematicians are not that original when it comes to naming variables. Now, to determine the truth value of more complicated statements, truth tables will become quite useful, which we'll define here. A truth table for a molecular sentence lists off all possible truth values for the constituent sentences alongside the resulting truth value for the entire molecular sentence. So let's return back to the sentential connectives. We'll start with the negation. The negation of a sentence denies the truth of that sentence by asserting it is not the case that whatever that sentence was. The negation of a true statement is false, and the negation of a false statement is true. In terms of symbols, here's the notation we'll be using. So if P is the original sentence, this little hook symbol stands for a negation. So negation of P would be written in this way. However, this is not the only one. Some books use tilde P to write the negation. Other books use minus P for the negation. All three of these are accepted, though I have a bit of a preference for the first one, so it's the one I'm going to use from here forward. If I want to write a truth table for this, here's how I would do it. I could write in P as my input and negation of P as being my output. If P is true, negation of P is false, as stated above. If P is false, then negation of P is true, as again stated above. So here's a complete truth table for the negation. So let's run an example of actually symbolizing this negation. So let's consider the statement below. He did not run around the corner. So what I'm going to do is I'm going to let P, the original statement, be the following, the positive statement, if you will. Basically the statement without the not, which is he ran around the corner. So here's how I'm defining P. Thus, negation of P would be explicitly this. It would be, it is not the case that he ran around the corner. Equivalently, you can shorten this down to being he did not run around the corner, symbolizing the original sentence at the top. Next, let's consider the conjunction. Recall, the conjunction of two sentences uses the word and to make a single sentence. The conjunction of two sentences is true if and only if both sentences are true simultaneously. In terms of notation, if P and Q are my sentences, some books use the wedge symbol in between right here to form P conjunction Q this way. Other books use the ampersand, so P conjunction Q can be written this way as well. Both of these are accepted, though I have a bit of a preference for the first one. For the truth table here, we have now two inputs. Since this is a binary operation, you have P and Q, and the output here will be P conjunction Q. As stated above, if P and Q are both true, the conjunction is true. Sadly, this is the only case where this happens. All the other cases, true, false, false, true, and double false, all yield false for the conjunction. Thus, we have the truth table for the conjunction here. So let's run an example of symbolizing conjunction. Consider the statement below. He ran around the corner and she followed him. What I'm going to do is I'm going to break this up into two clauses, and I'm going to conjunction the two clauses together. Specifically, P and Q will be the following. P will be the first clause, which is he ran around the corner. Q will be the second clause, she followed him. Consequently, P conjunction Q would be the following. He ran around the corner and she followed him, symbolizing the sentence at the top. Next, let's consider the disjunction. Now, recall the disjunction of two sentences uses the word or to make a single sentence. The disjunction of two sentences is true if and only if at least one of the two sentences is true. Now, if P and Q are my two sentences, P disjunction Q is written with this V symbol in between. So the disjunction is represented with this V symbol. P disjunction Q can be written this way. Now, notably, the V symbol here is the mirror image of the wedge symbol that was used for the conjunction. Now, why are the two symbols used together like this? Well, that's actually going to be explained in a later video. But for the time being, let's write out the truth table for here. Now, P and Q are my inputs. P disjunction Q is my output. So remember, if one of them is true, then the disjunction is true. So double true, true false, and false true, all of these have at least one of the sentences being true, so the disjunction is true. The only time a disjunction is false is in the case double false. So false disjunction false yields false, and here is the complete truth table for the disjunction. Let's do an example of symbolizing a disjunction. So let's consider the statement below, which is he drank a cola or she drank tea, which is the example from the last video. What I'm going to do here is going to be much like the conjunction example. I'm going to split this up into two statements and then disjunction the two together. The first statement here is going to be he drank a cola, which I symbolize with P, and she drank tea will be symbolized with Q. So P disjunction Q would be the following. He drank a cola or she drank tea, which symbolizes the sentence at the very beginning. Next, let's consider the implication. The implication, or conditional, uses the words if, then to obtain a single sentence from two sentences. The implication is false if the antecedent is true and the consequent is false. Otherwise, the implication is regarded as true. So, in notation, we write it this way. P implies Q, P is the hypothesis, Q is the conclusion, and the implication is written with this boldface arrow. However, this is not the only font of arrow that is used. Here's another arrow that is used also. Both of these are accepted notation, though I have a bit of a preference for the first one. So, when we write the truth table, we have the hypothesis, the conclusion, and the implication P implies Q. Now, the implication is false if the antecedent is true and consequent is false. Otherwise, it's regarded as true. So, when we build the truth table, true implies true is a true statement. True implies false is a false statement. That's the only time that it's false. False implies true is true, and false implies false is also true. Again, as stated, the only time that the implication is false is when the antecedent is true and the consequent is false. All other times, the implication is regarded as true, giving us this truth table below. Let's consider symbolizing an implication. Consider the statement below. If the cat knocks over the glass, then the soda will spill out. So as before, I'm going to split this up into two statements, P and Q, and then write down their implication. P will be the first statement, that is, the cat knocks over the glass. Q will be the second statement, the soda will spill out. So P implies Q would be the statement, if the cat knocks over the glass, then the soda will spill out, which symbolizes this statement at the beginning. Before moving on, I want to address one particular sticking point with the implication specifically. If you look at the conjunction, disjunction, and biconditional, they are what we would call symmetric, or they possess the commutative property. That is, if you swap the order of the operands, the calculation isn't affected by it. Now, we're going to talk about symmetry and commutativity a lot later, but I want to address the implication now as to why the implication is defined in such an asymmetric way. Why is it different than the other connectives? Well, it's because hypothesis and conclusion serve notably different purposes. For example, let's look at the last example I just talked about, the one with the cat and the soda. Let P be the statement, the cat knocks over the soda, and Q be the statement, the soda will spill out. The idea here is the implication is a causal relationship. The cat knocking over the glass causes the soda to spill out. So, what I want to do is go through each layer of this truth table and see what each of the situations are and why it either validates or violates the implication, and thus why it is regarded as either true or false. So starting at the top, true implies true, and that's regarded as validating the implication. And here's the situation. The cat knocks over the glass and the soda spilled out. So if the cat knocking over the glass causes the soda to spill out, then this validates that. This validates that statement because the cat knocked over the glass and the soda spilled. So the cat caused the soda to spill out. What about double false? False implies false. Why is this regarded as being true? Why is this validating the implication? Well, instead of validating it, let's regard it as not violating the implication. And the reason why is because the cat didn't knock over the glass, so the soda isn't spilled. If the cat knocking over the glass is a trigger for the soda being spilled, well, if you don't trigger it, then the soda didn't spill. So that doesn't violate the implication. And if it doesn't violate it, then it would be validating for it. Right? So that's what's going on in this case. Here's the case that's false. So true implies false is regarded as false, as violating the implication. And again, think about the situation. The cat knocks over the glass, but the soda does not spill. If the cat knocking over the glass was a trigger for the soda spilling, and the soda doesn't spill, well, it's not very much of a trigger now, does it? That violates the implication, which is why it's regarded as false. The implication here is false. That leaves, however, this one. False implies true is regarded as true, as validating or at least not violating the implication. So why is this one regarded as true as opposed to the other one? Well, here's the situation. The cat doesn't knock over the glass, but the soda spilled anyway. So why is this one regarded as not violating the implication? Well, the trigger isn't there. The cat knocking over the glass. The cat didn't knock over the glass, but the soda spilled anyway. So how can that be true? How can the soda get spilled if the cat didn't do it? Oh, it's because something else did it. So for instance, here's something that's happened to me. My cat is out of the room, and I accidentally knock over the soda. I accidentally swoop my hand, knock my soda over, and I end up having to clean up my own mess. So what's happening is there's another cause. For example, the cat is out of the room and I drop the glass and it spills all over the floor. So there are other causes besides the cat. So the cat may well be a cause. Is it the only cause? And no, there are other ways that the soda could get spilled over besides the cat. And that's what this truth table is taken into account. So true implies true validates it. So true implies false violates it. The bottom two do not violate. Therefore, they are regarded as validating. That is why the bottom two are regarded as true. Lastly, let's consider the biconditional. So recall the biconditional, or equivalence, uses the words if and only if to obtain a single sentence from two sentences. The equivalence of two sentences is true if and only if its members are both true or both false. So double true and double false are the only times this thing is true. For notation, we basically use the same symbol from the implication. What we do is instead of having a single-ended arrow, you have a double-ended arrow. So if and only if. So we have P if and only if Q could be written this way. But you can use other fonts of arrows, like say this one for instance. P if and only if Q can be written this way. But there is a third one in this case, which is this triple barred equal sign, the equivalence symbol. So P if and only if Q, or P is equivalent to Q. This symbol specifically emphasizes more that this is acting like equals in a sense. Now all three of these are accepted. I have a bit of a preference for the first, although very often I will be using the third just as much. For the truth table, the inputs here are P and Q, and the output will be P if and only if Q. Now P and if and only if Q will be true only when they match. So double true will be true, true false will be false, false true will also be false, and double false will be true. Again, it's only true if they match, and that gives me the truth table for the if and only if. Here's an example of symbolizing a biconditional. Consider the statement below. The car will be ready if and only if the fuel tank is full. As before, what I'm going to do is break this up into two statements and then put if and only if between them. The first statement P will be the car will be ready. The statement Q will be the fuel tank is full. So P if and only if Q will be the following statement. The car will be ready if and only if the fuel tank is full, symbolizing the original statement at the top. With these symbols in play, larger formulas can be constructed from them, what are called well-formed formulas by Magnus. A well-formed formula, or WFF for short, is defined recursively by the following rules. The first of which is every atomic sentence is a well-formed formula. So if you start with the building blocks, atomic sentences, atomic sentences on their own are well-formed formulas. So what happens next? How do you build other well-formed formulas? Well, what you do is you build them recursively from these pieces, using the following operations. If you have a well-formed formula, its negation is well-formed. So if P is well-formed, then negation P is well-formed. If P and Q are well-formed, then P conjunction Q is well-formed. If P and Q are well-formed, then P disjunction Q is well-formed. If P and Q are well-formed, then P implies Q is well-formed. And if P and Q are well-formed, then P if and only if Q is well-formed. And that's basically what you do. You start off with the building blocks, atomic sentences, and then you start applying all these operations of negation, conjunction, disjunction, implication, and by-implication. Although, Magnus's rules I'm going to tweak slightly. In Magnus's rules, he actually has parentheses shrouding each one of those well-formed formulas as they go along. Although I think parentheses are important enough to make a separate rule for them. If P is a well-formed formula, then shrouding P in parentheses itself is a well-formed formula. Magnus's original rule was that all well-formed formulas are formed by the above 6 rules, which I think is implied by the fact that they're defined recursively this way. So I'm going to essentially have parentheses be their own rule on their own. Let's give an example of building some well-formed formulas. So let P and Q be sentences. Then the following will be well-formed formulas. First, I will negate P. I'll then conjunction with Q. I'll then imply to P, shroud that in parentheses, and then if and only if with Q. Each one of these is a well-formed formula as I went down the row, just adding one piece at a time. Now, this does add some questions. This does beg some questions that we should answer in the next video. First, in what order should these connectives be performed? Is there a preferred order? Is there an order of operations? Next, how do these connectives interact with each other? So if you put two connectives on top of each other, does one have priority? Does one change the other one? How can they be manipulated? And lastly, are those parentheses needed? When can parentheses be omitted and ignored? And what are the circumstances when that can happen or can't happen? And that's where we're going to end for today. What we'll do next time is we'll pick up with some of those questions, actually talk about how to manipulate some of these connectives and how they interact. What we have here is a list of references. We have, again, Magnus's For All X, Suppes and Hill's First Course in Mathematical Logic, as well as Suppes's Introduction to Logic. Of course, if you like the video, please hit the like button below. If you have a comment or question, please leave it below as well, and we'll get to them as soon as we can. Thank you for your time, and we'll see you next time. See you then.